Okay, so here's some practice problems using these equations for the partition function, the translational partition function. So thermal wavelength practice. So what is the thermal wavelength and the translational partition function for argon at 1 atmosphere and room temperature? This condition of 1 atmosphere and room temperature, we call that standard ambient temperature and pressure, SATP. And that's not to be confused with STP. STP is standard temperature and pressure. So that A means room temperature. If you don't have the A, then it's 0C or 273.15 Kelvin. Okay, so mass, take it off the periodic table in grams per mole, you convert to kilograms, divide by Avogadro's number, and you've got the mass of an argon atom in kilograms. Okay, the thermal wavelength is given here. So you can put that mass in the denominator. You've got Boltzmann's constant, Planck's constant. Go ahead and write everything out. So this is the situation. You want to keep everything in SI units. So if it's a joule here, like this right here, if you look up Planck's constant, it should be a joule times a second. Okay. But a joule is a kilogram meter squared per second squared. And so that second squared times a second, you lose the exponent here. So you just have s to the minus 1. So that's why this has got just one s, second to the minus 1 there. So that's Planck's constant. Down here, Boltzmann's constant was a joule. This piece here is a joule per Kelvin. The per Kelvin cancels with this Kelvin. I've got the kilogram here, and I've got a kilogram here, and that's 2 kilograms, but it's in a square root. So it's kilograms squared, take the square root. It's a single kilogram, it cancels with that. Here we have per second squared, take the square root, it's only 1, s to the minus 1, so that cancels with that. And we have meters, let's see, meters squared here, but you take the square root, and so you end up with meters to the first power, and this is meters to the second power, so when you do that, it cancels one of those, and you end up with meters. So following the units will help you ensure to yourself that you've got at least a hope of getting the number right. Okay, but if you don't include your units, yeah, you're in trouble. So this is really small. So at room temperature, argon at 1 atmosphere, the thermal wavelength is 10 to the minus 11 meters. And so think about the partition function. It's the volume of the room divided by this number cubed. So it's going to be huge, a huge number. So if you have the volume, if we calculate the partition function, and I just said it's 1 atmosphere, so I said what is the volume of a gas, an ideal gas at 1 atmosphere, room temperature is 24.5 liters. So that would be the volume that it would take up at 1 atmosphere. So we can do the volume on top and the thermal wavelength on bottom cubed. And so this is the partition function for translation for argon at room temperature and 1 atmosphere. And look, remember what I just said today in like 2 videos ago was that the Q is a count of the energy levels that are populated. So in a 2-level system, when we went to high temperatures, it was 2. In a 3-level system, it would be 3. And in a molecule, you have infinite number of energy levels. At room temperature, we've already populated 10 to the 30 energy levels in argon in translational motion. So translation is quantized, but the spacing is so small. That's why we never detected it in spectroscopy. We don't have a spectroscopic technique that is that low energy that we could use because we're just in a hot world. Okay, so thermal energy is 200 wave numbers, and we're trying to measure something that's 10 to the minus, a lot. Okay, so that makes sense. That should be a huge number because translational motion is really difficult to even know that it's quantized. Now, what's the order of magnitude for the energy spacing? This is just a little side calculation. So just using the particle in a box calculation, what's the difference between E1 and E2? And it ends up just order of magnitude. Looking at powers of 10, it should be around 10 to the minus 18 wave numbers. And at room temperature, we have 10 to the 200. No, we have 200 wave numbers. Big mistake. So, we we definitely have what we call equipartition in translational motion, because the energy level spacing is 10 to the minus 18 wave numbers, and at room temperature we have 200 of thermal energy. So we have molecules in all of those translational motions, and in fact that's where we store heat in a gas, is we store it in the translational motion primarily. Okay, here's another calculation. This is a perfect kind of question I give on exams. You guys know me by now. If the translational partition for an unknown gas is 5 times 10 to the 30, what is it at 100 C? So at room temperature, 273, no, room temperature 298. What is it at 373 Kelvin, which is 100 C? And you say, yeah, but I can't calculate this. I don't know the particle mass. And I'm smiling, because you just need to do the ones and twos. You take the ratio of the two. You say that this is the crazy equation, but I can't do it directly because I don't have the mass. But I've got this proportionality. So if anytime you have a proportionality, you can take this and you can take like Q1 over Q2 is equal to T1 over T2 all to the 5/2 power. You have to take into account the power of the temperature, the dependency. And so this is our situation. We know the partition function for situation 1. We know the temperature for situation 1. We know the temperature for situation 2. We have one equation and only one unknown. And this is a skill that I ask on almost every exam in some way or shape or form, so that you get good at this kind of thing. If you know the proportionality, you can look at changes in the system. And that's the skill that I used the most when I got out of college. You have some crazy equation, but you almost never have all the information you need. But if you're wondering what happens if I change the temperature, that's easy to figure out.
Does this only work because it's a really high temperature?
No, this works even at low temperatures. Yeah. So if we put those temperatures in, we end up with it's 5 times 10 to the 30 at room temperature. It's 8 times 10 to the 30 at 100 C. So going from room temperature to boiling is not that much of a change temperature-wise, but we would have more energy levels populated.
Yes. So we had to use the information in the previous problem?
Mm-hmm. Well, it's just given there 5 times 10 to the 30 and room temperature. So yeah, even if we hadn't done the first problem at all, we're given Q1 and T1 and given T2 in the problem. So yeah.
This might be an arbitrary question, but at what point would we consider a very high temperature?
Whenever the temperature is, it kind of depends on the system, but a good rule of thumb, if the temperature is 10 times the energy spacing, right? So our energy spacing we calculated for argon was 10 to the minus 11 wave numbers. And so when we get to 10 to the minus 10 wave numbers of energy, then we would be at equipartition in translational motion for argon. So it's really hard to get quantum effects to come out of translational motion. And that's the next problem. So this is also the dependency. As temperature goes to 0, now this equation, notice we have that little tilde there. We made an assumption in coming up with this. It's not an exact solution. What was the assumption that we did when we went through? We went from a sum to an integral. We assumed that the difference in the quantum states was infinitesimal. When you cool the temperature down, now that energy difference is not infinitesimal. And so it fails down here. That equation will go to 0. Q will go to 0 as temperature goes to 0. But in reality, when you get really cold, what does Q do? Q goes to 1. So down at this end, don't be caught by that. That's sort of an approximation at high temperatures. At low temperatures, you got to go back to a discrete sum, and you can calculate it. So Q goes to 1 down on this end, but it goes to infinity on the other. So as temperature goes to infinity, so does Q. Okay, they just don't go at the same rate. I mean, it's temperature to the 3/2 power, so it kind of goes up pretty quick. Okay, and here it is for a water molecule. Same kind of curve. So it's nothing special about argon or super simple. Let's look at this one. This is kind of fun. if the translational motion is 5 times 10 to the 30 at room temperature, at what temperature would the translational motion be treated as a simple two-level system? So when we're asking, when would quantum effects emerge? Okay, and so we could use that as our second Q in that equation. So if we've got this equation here, we've got temperature 1, that's room temperature. Q1 is 5 times 10 to the 30. Q2, we want to know when quantum effects emerge. And so if we treat it like a two-level system, when does Q become 2? Right? So we could use 2 for Q2 and then solve for our temperature. So here we are. We put in, this is the room temperature Q. This is the Q when quantum effects emerge. It becomes a two-level system at that point, and it's room temperature here. So solving for this temperature in Kelvin is 2 times 10 to the minus 10 Kelvin. So it's extremely cold. So we're not going to see quantum effects in translation, in our everyday experience. They are getting close. Okay, so they're getting close with this idea of what's called a Bose-Einstein condensate. And they're getting to 10 to the minus 6, 10 to the minus 7 Kelvin. And they're starting to see nature act weird. Okay, so you can look up videos on Bose-Einstein condensates. I think I'll probably put one in the playlist. And I've got one queued up here, but I won't record it because I don't want to get copyrighted.